Hi, everyone. My name is Matt. I'm a researcher at Google on the Brain team, and today I'm going to talk about JAX. So to motivate JAX, we're going to start with a question, which is how might you implement a deep neural network from scratch in Python? So forget about all the neural network training libraries you know. How would you do it from scratch? So when you're doing anything numerical, a good idea is to reach for NumPy. And you can write a simple neural network in NumPy just in a few lines, calling functions like NumPy dot and doing some NumPy element-wise nonlinearities. So that'll give you a fully connected neural network. And then you can write a loss function in another few lines. In this case, maybe a squared error loss function. And so you might ask, if it's so easy to express the programs involved in neural networks with just NumPy, what's missing here? What else do we need? So one thing we need is we need the ability to use accelerator hardware like GPUs and TPUs. But that's just the start. We also need things like efficient automatic differentiation for doing optimization and training. We might want to be able to stage out to an optimizing compiler that can do optimizations like fusion and memory layout and rematerialization. We might want, for an advanced algorithm or something like differential privacy, we might want things like automatic vectorized batching of operations. And finally, we might want to parallelize over multiple accelerators. So JAX is about adding these missing things. It's about saying, NumPy is such a great tool. Let's keep writing code with NumPy API, but let's add in these extra features. In particular, JAX uses the XLA optimizing compiler to be able to project your code onto hardware accelerators. And then the main action in JAX is actually in these function transformations that are at the bottom of the screen here. These are things like automatic differentiation or just-in-time optimized compilation or things like vectorized batching. So to give you more of an idea of what that actually looks like, we're going to jump into a lightning-fast demo. All right, so here is our Colab notebook, and we're just going to take a look at JAX. So the place to start is NumPy running on a GPU or a TPU. In this case, it's on a TPU, but JAX code looks the same no matter what you're running on. So let's start by importing jax.numpy as JNP and importing JAX, and we'll just generate a big random matrix. So it's a 5,000 by 5,000 float 32 matrix. And then we'll start doing NumPy things. So we can do matrix multiply. We can print out the first coefficient of the result. We can do transposing, of course. We can do fancy indexing, and all these things sort of work. You might, think that you're using the original NumPy. One way you can tell that you're not, though, is if you do a simple timing benchmark. So to multiply this 5,000 by 5,000 matrix by itself, this JAX NumPy running on a TPU is doing it in 12 milliseconds. Maybe, an optimized NumPy build on a really fast CPU could do it in 250 to 300 milliseconds. So this is running, quite quickly. This block until ready on the end is because by default, JAX will execute operations asynchronously in the background and only block the sort of main Python thread or pull values back to the CPU if they're needed for printing or plotting or Python control flow or saving to disk, this sort of thing. And so for micro benchmarks, we just add this block until ready on the end. But yeah, this is how we're using JAX NumPy and running it on a hardware accelerator. So that's great. But as I mentioned before, the real action with JAX comes in these function transformations. So the first one we'll look at is for automatic differentiation, and that's called grad. So let's import grad and write a simple Python function here. So this Python function has some Python control flow. If x is greater than 0, return one thing. Otherwise, return this other thing. Grad is a function transformation that takes a Python callable and gives you back a Python callable. If you give it a Python callable that evaluates a mathematical function f, it gives you back a Python callable that evaluates the gradient of f. And so we can just call grad of f and run that. We can exercise both sides of the control flow. And indeed, we're just getting the gradient of this simple scalar function back out. One nice thing about this sort of function-oriented view of automatic differentiation is that it's easy to do higher order differentiation. So in this case, we can just apply grad to its own output, apply it many times, and then we're doing higher order differentiation. So obviously that's a very simple toy example, but we can also just go to that neural network code, that simple neural network that we wrote on the first slide. Here it is. And here's just some simple code to initialize it with totally random parameters and random input data. So this is just all a toy model. So we have our loss function. We can evaluate it on these randomly initialized parameters in this random data. We get some value out, and we can run a simple gradient descent loop. So we're using the gradient of the loss, and we're taking small steps in the negative gradient direction to minimize our loss. And in this case, our loss has indeed gone down. So that's great. So JAX has a lot of advanced autodiff features. This is maybe the simplest demo, but if you like autodiff, you should definitely take a look at JAX. It has all kinds of fancy stuff that I don't have time to go into. But for now, instead, let's look at our next function transformation. So the next one is end-to-end optimized compilation with the XLA compiler using the JAX transformation JIT. So in this case, again, we have a function that takes in a Python callable and gives you back a new Python callable. So we're making the loss JIT version of the loss function. And we can see that if we call it, it has the same input-output behavior as our loss from before. In fact, we're getting the same numerical value out when we call it. The difference is in timing. So if we time how long it takes to execute the first version of the loss, because it was sort of executing every operation on its own, it's somewhat slower. The JIT optimized version of our loss function is dramatically faster. Not only is this staging out of Python, so there's no Python overhead, but also XLA is an end-to-end optimizing compiler. And so it's performing all these optimizations like optimizing memory layouts and performing fusions and these sorts of things. So can execute much faster. And we can do the same thing to our gradient function. So we can JIT our gradient function, and indeed that's very fast as we might expect. And we can do another set of steps of gradient descent, and indeed this version executed much more quickly, and our loss is still going down. So that's great. So that's JIT and grad, putting them together. Already we can do some nice neural network training at pretty high performance. I wanted to show one more transformation though. This is VMAP. VMAP is actually oftentimes people's favorite transformation when they start to learn JAX. Let's import it. So what VMAP does semantically is very much like a map or just sort of a loop over your function. And so here we can say we're VMapping a function that just performs squaring over an array, and it's just as if we've sort of mapped that function over the array. What's different about VMAP is how this map is computed. So what VMAP does is it vectorizes your function by plumbing the sort of extra mapped dimension through all of the operations in your code. For example, turning matrix vector multiplies into matrix matrix multiplies. And so this is exactly as if we had done the batching by hand, but we can do it automatically. And so, for example, if we wanted to compute per example gradients for differentially private training, we can do that. We can compose grad with VMAP and JIT the whole thing. And then here we can compute per example gradients. Here we have a batch size of 128. Those are the gradients with respect to our first parameter there. So those are just a few transformations scratching the surface of JAX. I don't have time to go into details, but you can really gain a lot of power by composing these things up. So for example, the best way to compute Jacobian matrices, dense Jacobian matrices, and Hessian matrices is to compose these things together. Here we're composing forward mode and reverse mode and VMAP twice, as well as JIT. And this is sort of the most efficient way to compute dense Hessians. So that's it for our first demo. I just want to tell you briefly about some of the exciting research that's been done with JAX so far. So it's being used for research on vision transformers, which is really exciting. It's being used for research on neural radiance fields. So we have these incredible visualizations that come out. It's used also for things like molecular dynamic simulations. So when these folks are having fun, they simulate shooting a bullet at the JAX logo. But when they're doing more serious work, they're doing things like optimizing material properties using JAX. It's being used to great effect at DeepMind, for example, to solve the Schrodinger equation much more efficiently. It's also being used for the next generation of work on reinforcement learning agents. Actually, this is a research project that I collaborated on. This is for neural ODEs, making them fast to solve. And what was really exciting about this is, again, we were able to compose up a whole bunch of JAX transformations to great effect. So that's some great research, but what about scale? This conference is all about scale. So one thing we did to sort of push JAX at scale was we entered the MLPerf competition in 2020. This is sort of the big competition for training neural networks at scale on supercomputers. There's entries from all sorts of different companies. And so we made 4 submissions in JAX, and they were all 1.5 to 2.5 times faster than the next fastest non-Google submission. In particular, what was really exciting for one of my teammates who worked on this was this transformer benchmark where JAX set a clear world record. And for him personally, it was a 50,000 times speed up over the work that he was doing on a sort of top of the line GPU rig 5 years ago, where it went from taking 7 to 10 days to train to taking 16 seconds to do this training of a much more sophisticated model, a transformer model, on this benchmark data set. So that was for a benchmark competition, but what we want to do now is bring this kind of scale to a lot more users. And one of the ways we're doing that is by leveraging cloud TPUs. So cloud TPUs are these accelerator chips. Each cloud TPU has 8 cores, and you can think of it as being attached to a single CPU host, together with lots of high-speed interconnects between those accelerator chips. And the XLA compiler is actually designed for targeting these things really effectively. Now, that was a single cloud TPU, but a cloud TPU pod is many of these things hooked together. And what's really interesting is that all of those accelerator chips have fast inter-chip interconnect between them, actually in a sort of toroidal topology. And the XLA compiler is also really good at targeting these big supercomputers. So the way to think about how these machines look is that we have all of these accelerator chips that are networked together amongst themselves, and then we have these CPU hosts off to the side. And what we need to do as programmers is somehow launch JAX Python processes on all of these hosts, and then use that to drive all these accelerators that will talk amongst each other on these fast interchip interconnects. So to show you what that's like, we actually prepared a demo. So let's take a look at driving one of these TPU supercomputers using Ray. So we're SSH'd into our one of our worker nodes here. We're going to import Ray and just initialize a Ray cluster. So we already have Ray running on all these 128 TPU worker nodes. So we're connected to 1,024 TPU cores. And we're just going to write a simple Ray function that's going to import our MLPerf training code and run it. And we've set this up so that we'll call this 128 times for all the 128 hosts. Ray will balance that onto all the different worker machines, and then we'll start running things. So actually, initializing the cluster takes about like 2.5 minutes, and the compilation step takes about 1 minute. And so through the magic of television, we have sped up those steps. But all this training right now is in real time. So this is exactly as if we're running MLPerf. This is a smaller machine than we ran for the MLPerf. But this is now running, each epoch is running this WMT English-German data set. So about 4.4 million parallel sentences, and with a global batch size of 2048. And so we're running these steps very quickly. And the MLPerf target blue score is 25, or sort of an eval accuracy of 0.25. And here we can see we finished training in just 38.35 seconds using this TPU supercomputer and Ray. So if you'd like a more detailed look at that same demo, check out this tweet linked here. And you can see a bit more into the guts of how all that works. Great. So that was a whirlwind tour of JAX and how it's a system based on these composable function transformations meant for accelerating machine learning research. And we're really excited about driving this supercomputer scale and bringing it to more people. So thanks for your attention.